Assalamu alaikum students. Today the topic which we are going to study is star to delta connections in the three-phase transformers. Star to delta connections in three-phase transformers. Connections in three-phase transformers. We will mainly talk about its Phasor diagram, right? What is meant by Phasor diagram? The Phasor diagram means, as I have told you previously, that we have the three sequences: the positive sequence, the negative sequence, and zero sequence. Okay, so in order to conduct this lecture, I'll first draw the fundamental diagram in star to delta or Y to delta connection, right? So let us draw the diagram. It will become just like this. This is the terminal, and here it is. This is first one, and here it is N terminal. Here we have this thing as B terminal, here A, B, and this one is C terminal, right? Likewise, here on the other hand, we will draw this thing. Along with this, we will draw this in the form of a delta connection, right? So here we have A, B, and C, right? This is B connection. Here we have the C, and at the topmost we have this A, right? Now we will mark the terminals A, B, and C terminal. Okay, and here we have this thing is IA. Here we have this as IC, and here IB. Just like this, we will draw here IB, IC, and here IA. Okay, so IA, IB, and IC, right? So we will have this thing, and after it, what we will draw? We will have this IAB. Here we have this IAC, and here IBC. Also, this is A, this is B, and here we have this is C, right? So now we will define the polarities here and this one, right? Just like this, we will draw here, and at this point there will be another polarity, right? So coming on to the point that according to the American standard of designating terminal, terminals, what we will have here, the terminals will be named as H3, H2, and H1 on the primary side, on the high voltage side, whereas on the lower voltage side, on the secondary side, we will have X1, this will be X2, and here we will have this as X3, right? So H for high voltage side and X for low voltage side. Okay, now you have understood that how I have drawn this diagram, and after drawing the diagram what I have found, right? So now, as you know that H1 to neutral leads to X1 to neutral by 30 degree, right? H1 to neutral, this one, this whole, this terminal from H1 to N, right, means the voltage AN, right? We can write H1 to neutral leads the X1 to neutral by 30 degree, right? As you know that there is no neutral inside the delta, but under the balanced voltage conditions we consider the ground as a neutral, right? So in this particular case, the H1 to neutral means to say the voltage AN will be leading the voltage IAB, the neutral, the voltage across AN will be leading the voltage across the X1 by 30 degree, right? Now likewise, it's correspondingly the voltages across voltage drop across terminal H2 and H3 will be leading the voltage X1 and X2 by 30 degree, leading the voltage across terminals X2 and X3 by 30 degree each respectively, right? So after it, as you know that for the positive sequence what we will draw is VAB. You know the voltage across this terminal VAB will be in phase to this AN, right? As you know that VAN or VA1 for the positive sequence will be in phase to VAB, right? So we will write here just like this, VAN1. You know, as I have described during the symmetrical faults, that VAN1, this superscript of 1 is showing positive sequence, while the superscript 2 is showing negative sequence, right? Here it is negative sequence, and here we have this as 0, right? So in this case, VAN and VAB will be in phase, right? So due to this we will draw it just like this. How we will draw it? it will become just like this, that VA1, as you know that this line is VA1, we will consider it as the fundamental identity. So VA1 and VAB, right? VAB, we will write here 1. Both of them are in phase. So first of all, what we will do is to draw these two vectors, right? VA1 and VAB1, as these two are in phase, right? So first of all, we will consider them as the fundamental vector identity, and we will draw them on the paper, right? After drawing it, what I will conclude is that VB1 lags the voltage by VA1 by how much? By 120 degree, right? So as we know that VB1 lags voltage across VA1 by 120 degree, VA1 by 120 degree. Then in this particular case, the VC1 lags, then VC1 lags VB1 by 120 degree, right? So now we will draw it. If we will draw, we will come to notice that it will be noticed that the VB will become 120 degree here and VC will become 120 degree here. And generally, when you will draw it, you will just draw it just like this, that this is A, and after it we will draw it at the 120 degree phase difference, we will draw B, and then after the 120 degree more, means at the 240 degree from the vector VA, we will draw VC, right? But in this particular case, what happened, that we have picked this particular difference of VAB, and then we have placed it here, right? So this is VB1 and this is VC1, right? Now as you know that so it will be concluded that VB1 as the VB1 lags the voltage across VA1 by 120 degree and VC1 lags the VB1 by 120 degree. Therefore the tips of these arrows will meet at a point. Therefore the tips of these three vectors will meet at a single point. Okay, so as you know that in this particular case the tips are on the single point, right? So after it, what we will have, this VB1 and VC1, right? This VB1 and this VC1. So let me tell you that for the low voltage side, VBC1 and VCA1 can be drawn in phase to VB1 and VC1 respectively. Let me show you how. First of all, let me write the statement and then we will draw it. For low voltage side, VBC1 and VCA1 can be drawn in phase 2 VB1 and VC1 respectively. Okay, here you have to remember that this VB1 and VC1 both are present on the primary side or on the high voltage side. Okay, afterwards the line to neutral voltages can be drawn. Afterward, line to neutral voltages can be drawn, right? So this is our statement. Now we will implement this statement onto this vector, right? As you know that I have said that VBC and VB1 are in phase, right? This VBC and VB1 are in phase. So what we have here, VB1 is drawn at the 120-degree angle of difference from the VA1. So how we will draw it? We will draw it just like this, that VB1 is, if we have this VB1 here, then VBC1 will be drawn just like this, right? And this, the other one is VC1, and VC1 is having the same direction as VCA. This VCA and VC1, right? So these two are having the same direction. So what we will draw, it will become just like this. Okay, so this is the first step. Here we have this is A, this as B, and this as C, right? So let me write here that it is VBC1 and here VCA1, right? So our statement which we have written is satisfied till this point, till up to respectively. Afterward, line to neutral voltages can be drawn, right? Line to neutral voltages will be drawn on the which side? Secondary side, right? Whereas line to line voltages will be drawn on the primary side. Okay, line to line voltages will be drawn on the primary side, on this side, and line to neutral voltages will be drawn on the secondary side. Why line to neutral voltages will be drawn onto the secondary side? Because we have delta connection on the secondary side, right? So delta connection, in delta connection we always prefer line voltages, right? So first of all, line voltages are drawn. In Y connection we always prefer line to neutral voltages. So in this case, this VAN and VA1, these are equal, these are known as single identity, right? Or single entity. So we have this VA1, VB1 and VC1 present here. So we will now draw vector just like this, right? And here the second one just like this, right? And the third one will be just like drawn just like this, right? So this is in the its arrow will be downward, right? So here we have this one as VBC1, here this is connecting between the 2 points VA, this is VB, and here we have this is VC. So this is VAC, VAC 1, right? So if we consider this, we have to place this superscript of 1 here so that it can be depicted that we are drawing the positive sequence diagram, right? So in the other case, on the other hand, on the secondary side, we have to draw line to neutral voltage. So in this particular case, we will again notice that this is VA1, so we can draw this VA1, right? This is from the terminal B, again it will become VB1, and here from the terminal C it will become VC1, right? So these are the neutral voltages, right? So it is very easy to draw. From the terminal A to neutral, this will be VA1. From terminal B to neutral, it will become B1, and from terminal C to neutral, it will become VC1, as I have shown here, right? So this will be the whole scenario when you will draw the phasor diagram in the first phase, right, for the positive sequence. Now moving on to the negative sequence. Now for negative sequence, for negative sequence, where negative voltage is applied across terminal A, B and C, it can be noted from the dots, from the polarity, that VA2 is in phase with VAB2. As you know that this, now it will become VAN will become VA2, and this VAB will become VAB2. How it will become VAB2? Because for the positive sequence, when we were dealing with the positive sequence, we have placed the superscript A here, right? While when we will draw the negative sequence, we will change this to superscript 2, right? So I can write here that for negative terminal, means when negative voltage is applied to terminal A, B and C, it can be noted from dots. It can be noted from dots that are showing polarity that VA2 is in phase with VAB2, right? So in here we have this as small because it is on the secondary side, right? So in this particular case, it is not necessary that VA1 and VA2 are in phase, right? Means the positive sequence and negative sequence can't be in phase necessarily, right? If you can consider them in phase, it is okay. If you are not considering them in phase, then you have to draw the figure accordingly, right? But it is more preferable to keep VA1 and VA2 in phase, because it makes our work relatively less complex and less complicated as compared to placing them on the different phases with the in order to synchronize them with the different phases, right? So here we have the next thing as VA2 is in phase with VAB2, right? So correspondingly, VB2 is in phase with VBC2, and VC2 is in phase with VCA, okay. So similar to the positive sequence, first of all we will draw the line voltages on the high voltages side, and then the neutral voltages can be drawn on the low voltages side, right? So but before doing this, we have to draw these VA2, VB2 and VC2, right? So similar to positive sequence, the line voltages can be drawn on the positive or on the not positive, on the high voltage side, and neutral voltages can be drawn on the low voltage side. Voltage side, or we can say it secondary side, right? So let me draw this figure so that you can understand it. Based on this statement that for negative terminal, when negative voltage is applied to the terminal A, B and C, it can be noted from dots that are showing polarity, that VA2 and VAB2 are in phase. So we will draw the figure as VA2 and VAB2, right, as these are in phase. So now, as you know that the tips are equal, so this will become VB2 and it will be in phase to VBC2, right? VB2, and therefore here it is C, and this will become VBC, VBC, okay. Now as you know that the third tip will be of VBC, C2, right? So we have considered this as VC2. Now this VC2 will be in phase to VCA2. So here we have this as A2, here we have this as B2, and this one is C2, right? So this will become just like this, right? So it will become VAC2. So now we have drawn it just as required. So this will become V. Now we will draw the line voltages across the primary side and neutral voltages across the secondary side, right? So for this purpose we will write here C2 B2, and now we will connect this just like this, and here for the third terminal we will make it just like this, right? So here we have this thing as the arrow will be on the top side. Sorry, I have cut it bit while drawing. So this is VBC2, here we have VAC2, and there we have this as VAB2, right? So now we will draw the directions that VA2 and VAC2 will be in phase. Likewise from B you can again go to this neutral point, right? This will VB2, and here from C it will become VC2, right? So in this way we will draw our figure. This is VA2, here we have this as VB2, and here the upside down vector, this is known as VC2, and this is basically we have the neutral point or N, and here we have this as larger N, right? So in this way we will draw this figure of the negative sequence. Now if we consider that N1 and N2 represents number of turns on primary and secondary sides, respectively, then according to figure A of positive sequence we can write A of positive side sequence. Sorry, we will not write this side, it is positive sequence. Then we have VA1 is equal to N1 divided by N2 into VAB1, and likewise for the negative sequence it will become VA2 is equal to N1 by N2 into VAB2. Okay, so in this particular case, the above equations, if implemented over a vector sequence of B and C, right? So these two equations above equations, if implemented over vector sequence of figures figure B and C, it means to say this is figure C, while the previous figure of positive phase sequence is known as figure B, while the basic figure, the fundamental figure in which we have drawn the star to delta connection, it was considered as figure A. So in this case, above equations, if implemented over the vector sequence of figure B and C, it means that if we implement it over the positive and negative sequence respectively, then equations become VA1 will become N1 divided by N2 into under root of 3 and VA1 into angle of 30 degree, while VA2 will become, VA21 is equal to N1 divided by N2 into under root of 3 VA2 into minus 30 degree, right? How this one becomes, because we have this 30 degree, as I have told you in the previous slide, in the start of the lecture, that VA2 and VA, and that the voltages on the terminal, on the primary side of the terminals, are leading the voltages across the secondary part of the terminals by 30 degree. So that's why we have 30 degree here and minus 30 degree right over here. Okay, so now we can write that during Y to delta or delta to Y connection, transformer, during Y to delta or delta to Y connection transformer, voltage is leading by 30 degree during positive sequence, when a transformer is performing a step up function, is performing a step up function, right? So how we can implement this statement mathematically? We can implement in this way, that we can write as VA1 is equal to VA1 into 1 into angle of 30 degree, right? Therefore IA will become IA1, we have to write it in the positive sequence first. IA 1 into 30 degree, and the other case we have is VA2. This will become, for the negative sequence, VA2 into 1 into minus 30 degree, and likewise IA2 will become IA2 into 1 into angle of minus 30 degree, right, as you have learned it from here. Okay, so now we can say that, so we can write here that as VA1 divided by IA1 is equal to VA1 divided by IA1. So we can write here that VA1 into IA1 is equal to VA1 into angle of 30 degree multiplied by IA1 into angle of 30 degree, minus 30 degree, right? Then we can have this as VA1 into IA1. Let me tell you here that in this particular case it is IA1 static, because usually power flow that is associated with active and reactive power not get affected due to phase shift, as the current phase shift compensates exactly for the voltage phase shift as far as the power values are concerned, right? Compensates the current phase shift, compensates the voltage phase shift as well as not as well, but it is as far as as far as power values are concerned. Power values are concerned. Okay, so in this case, writing the per unit values will become this. Basically, this form is of complex power, right? So we have written this complex power. This is basically how it happens, that this is basically the complex power formula for the positive sequence, in which VA1 is multiplied with the IA1, and here we have this this is IA1 static, and here we have VA1 into IA1 static, and it will be lagging. This current phase shift will be lagging behind the voltage phase by 30 degree. So we will have this thing, and afterwards these two will be product VA1 into IA1, while the addition of these two phasors will result in 0, right? So we have not mentioned 0 here, we have only written VA1 and IA1 here, right? So now it is important to note that current ratio of any transformer with phase shift is reciprocal of the complex conjugate of the voltage ratio. How? That let me tell you that the positive sequence of IA1 to the on the higher voltage side to the ratio of IA1, the positive sequence across phase A, and the positive sequence current across phase A on the secondary side, on the lower voltage side, will be equal to VA1 static divided by VA1 static, right? And its whole inverse, right? From this equation you can find out this, right? It is very easy to calculate. You can calculate it yourself. Okay, so this is now we can say that it shows that current ratio of any transformer with phase shift is reciprocal of complex conjugate of voltage ratio. Basically, these two stars are representing the conjugate, and from this main equation of the complex power we can depict that this IA1 divided by IA1 will be equal to conjugate of the voltage ratio from the primary side to the secondary side, and then taking its whole inverse, right? It will become in this form, and it will getting this equation. This equation will be satisfying this statement, right? So you must have to remember this all, and this is all from the today's lecture, and we will progress on to the next lecture from the auto transformer as well as the other things in the next upcoming lecture. Okay, thank you very much.